with finishing up lecture questions 5 and 6. And I decided to move this group's question into the lab because we're going to be, in a way, talking about these, but when we do spirometry, because we're going to come back to these volumes. So let's look at question 5. It says, explain why rapid, shallow breathing, hypoventilation, can move the same amount of air as normal breathing and yet have poor air exchange. So first of all, let me share with you the lecture slide that has to do with this. Now, you don't have to be able to use these numbers, but at least understand why it's so much less efficient to have hypoventilation versus normal rates, depths of ventilation. Now, one of the things I want to stress, because this is confusing for a lot of students, is if you see hypoventilation, you are talking not about the rate, but a decrease in the volume. It says nothing about the rate. It's only talking about volume. And if you're seeing hyperventilation, it's talking about the increase in volume. So rate is certainly a factor, but you're going to see with hypoventilation why, even though you breathe faster and therefore move the same amount of air from outside in the atmosphere into your alveoli, your efficiency becomes very low. Now, why this is important is because many patients will show up with a symptom of hypoventilating, where they have rapid, shallow breathing. So what I'd like you to do, and we did this, I know, in the lecture slides, but because today we're going to be measuring some of these volumes and calculating some of these numbers, it's good to understand them. And this puts them in context of something that could be relevant medically. So here's a normal person. Now, this dead space volume, if you recall, maybe I'll put that here, the dead space volume is the part of the residual volume, the immovable air volume that is in the conducting zone. Sorry, maybe if I grab this and move it, if it will let me grab it. Oh, well, grab it and move it. No, it doesn't want to let me do that. Hopefully you got that. So here that person is about 150-pound person. And roughly speaking, you can't measure what's in the conducting versus you can't actually measure the residual volume at all. But the size of the person will affect how long is their conducting zone. And therefore, you can kind of roughly use body weight in pounds equivalent to the number of mLs of conducting zone. Clearly, someone who's short and very stout, that's not going to work. But an average build person, the taller they are, the longer their conducting zone. So we're going to assume this 150-pound person, and as I believe it was Dina pointed out, and their normal respiratory rate would be 12 to 15, but to make this math easier, they upped it to 20 breaths per minute. So that's an abnormal number, but it does make the math easier. So if you multiply 20 times their tidal volume of 500, that will give you what's called a minute respiratory rate. So about every minute, they move about 10,000 mLs. Now, when you go to do the spirometry tests, they're going to use liters rather than milliliters. And the book tends to use milliliters, as long as you are comfortable recognizing the conversion. So if it shows up as liters or it shows up as milliliters, you understand how to convert this. So this is about, 10 liters. Now, because they are, as they're breathing, remember they're doing 20 breaths. Each time they breathe, they have to replace all that air that's in their conducting zone. Yeah, it mixes with the old and all like we talked about, but remember, if they move a certain volume, like 500 mLs in, then 150 of those ml, of those 500 mLs, is left behind in their conducting, in their dead space, in their conducting zone. So in fact, for each breath, instead of 500 mLs reaching their alveoli, only 350 of those reach the alveoli, 150 stay in the dead space. Since they're doing this 20 times in a minute, 20 times 350 only actually gives you 7,000. That makes it to the point where the gases can exchange within the alveoli itself. So at rest, this person, well, I guess they're at rest with that rapid respiration rate, but is about 70% efficient. 70% of the moved air actually makes it into the alveoli. The other 30% stays in the dead zone. So why this becomes important in hypoventilation is if you breathe rapidly but shallowly, even though you move the same amount of air, you still have to each breath leave the same amount in the conducting zone. So this person is only breathing in 250 mLs with each breath. We have to subtract 150, which means that only 100 mLs for each breath is making it to the alveoli. To try and increase that, the person is going to breathe faster, so they've doubled the respiratory rate, but even then, their efficiency drops significantly. So you might say, why don't we breathe fast, slow, and deep? Well, because as you are studying now in lab, it takes accessory muscles to do that, which you may be wanting to use for something else, or you just don't want to burn that much ATP by using these accessory muscles. So remember, hypoventilation is really talking about volume, because when you hypoventilate, you're less efficient. Your negative feedback loop that we're going to talk about next lecture is going to cause you to breathe faster, and it will try and cause you to breathe deeper. The reasons for hypoventilation may be that you are totally congested in your conducting zone and mucus is covering everything, and therefore it's hard to get the gases through. Resistance has gone up, or you have a massive allergic reaction and histamines caused constriction of the bronchi, and therefore it's hard to get gases through those areas. So if you are affecting, ventilation, then these are called, obstructive diseases. I can't type. So that means something like asthma, where you have maybe both, a major histamine release so that the bronchi are all constricted, and then mucus increases, the secretion of mucus and secretion increases and makes the resistance go up and the diameter go down even more. Other chronic COPD is often a chronic version. COPD stands for chronic obstructive pulmonary disease. So those things like early emphysema that you're drawing in the slides is an example of that. And that arises because emphysema arises because the elastic fibers around the alveoli in early stages lose elasticity, and that's often because they get damaged. The alveoli are damaged and have scar tissue. replace them in, say, something like someone who has asbestosis, and they, in early stages, the asbestos that they inhaled has caused some scarring and less elasticity, just like in blood vessels where you have scarring and they have less elasticity. And that means that not so much when they inhale, because they can try to inhale more and stretch these less elastic, less compliant alveoli. But when they go to exhale, relaxing the muscles isn't enough to actually decrease the volume a lot. So what you'll see in that slide is, I hope, is that the alveoli look larger. And that they look larger because they're unable to rebound back to their original size. What that means is that the person's going to have a higher residual volume. So more old air is in there. As they try to breathe in, there's less fresh air to old air mixture, and therefore their partial pressures get affected in that case. Same thing with early fibrosis of the lungs. It's a COPD where, again, more scarring. Now, as the disease progresses, it can then replace the type 1 cells with pure scar tissue. So you're not able to do any kind of air exchange across that alveoli, and you actually lose lung capacity. When you lose lung capacity, you're talking about restrictive diseases. I'll put alveoli capacity. I can't spell, can I? Restrictive diseases, as a general rule, mean you have less residual volume overall and less total lung capacity. So we'll come back to that with a handout, but if you have asbestosis and eventually all you get is scar tissue in parts of your lung, there's no more alveoli, they're active, you can't inhale as much. You can't, not just because you can't ventilate, because there's nowhere for the gas to go, and you have less exchange surface, and those are restrictive diseases. So you can see from what I'm saying that there is a bit of the same disease can eventually start as obstructive and lead to restrictive. Okay, so that's 5. And a bit of 6. The other terms in 6, dyspnea, that just means difficulty breathing, labored breathing. It's a sort of general term without giving it's a description of a sign of somebody not having a problem. It's not telling you what the underlying kind of cause of the problem is. And the other 2 were defined in the lecture. So I think you can handle that, where stridor is where you're hearing this high-pitched sound, and rales, you're hearing a wet sound, which are, again, these are symptoms or signs of what could be the underlying disease problem. Okay, so we'll talk about obstructive and restrictive a little bit more in a few minutes. So let me stop sharing this, and we'll go over, and I have it over here, and I'll share the handout. Here it is. So you have this, I hope. And what I've shown here is just the background, where, again, I discuss these 2 broad categories. Now, a spirometry is a tool that helps but does not definitively diagnose obstructive versus restrictive diseases. This is really supportive evidence that has to fit into the picture of the patient as a whole of their situation. So it's often used to monitor the progress of some of these diseases. You also can run into spirometers with any patient that's bedridden or in the hospital or unable to move around a lot, because what they do is they try and have that patient breathe as forcefully as possible into these little plastic spirometers. They're not using that to measure all these volumes like Kevin does in the people in the other videos are discussing. They're trying to get your lungs to inflate maximally and exhale maximally so that your lung capacity doesn't get affected, fluid doesn't accumulate. When you're breathing in and out, you're helping to expel fluids, that come out with your expelled gases. And, if you don't do that enough, then there's a chance that pathogens can infect the lung, and you could end up with, say, pneumonia from being bedridden for a long time. So it's kind of a preventative activity that the person is doing. So what this says is, again, it defines obstructive versus restrictive diseases, and then it talks about them in terms of some of the things that were discussed in the lecture on Tuesday. Total lung capacity. Remember, total lung capacity is both the immovable air, which would be affected by, say, restrictive disease because you don't have as many alveoli pockets to fill, and all the movable air as well. So vital capacity is a measure of just your movable air. Now, what you're going to see in the video is they're going to be calling something functional vital capacity versus vital capacity. There's not really a difference in the numbers. The difference is really, are you measuring it like Kevin does, where you do a maximal inhale and then you measure the maximally exhaled volume of air? That's a functional one, as opposed to one where you measure individual things like tidal volume, inspiratory reserve volume, expiratory reserve volume, and you add those numbers up. So if you're looking at one person's inhale and rapid exhale, maximal exhale, that's the functional one. And really, you can use them pretty interchangeably, but that's why they use that term, just to be clear. So similarly, when they add the functional expiratory capacity, that is the single event where they've forcefully exhaled after a normal tidal volume has been exhaled. Now, you can't really measure that very easily. So and he doesn't go through all of these measurements, because you don't know when to stop your tidal volume and say, okay, I'm done with my tidal volume, now I'm going to measure the rest. So instead of measuring volumes, very often these machines measure what are known as capacities. So just like vital capacity is a sum of tidal volume, inspiratory reserve volume, and expiratory reserve volume, when you see the word capacity on it, you're looking at the sum of more than one kind of volume. So hopefully that is clear as we go forward. And if you look at your lab manual, that nice graph that's showing tidal volume, inspiratory, you can see, if you look at it, they define all these, they give all the numbers, and you should be studying that for the lab test, that graph. And you'll see capacities are sums of multiple volumes. Okay, what it talks about here is restrictive diseases generally decrease the air in the respiratory zone, that is the total lung capacity, as well as the total volume you can move into the lungs, the vital capacity. There's less lung tissue. Usually, though, they can expire fairly well, because you may not have changed the compliance depending on the disease, the compliance to exhale air. And tidal volume, which is just the relaxed breathing, might not be affected either. So you don't use your maximal capacity when you're just relaxed breathing. So even though it's diminished capacity, usually you can still move about the same air. I mean, you'd be in a lot of trouble if you couldn't. So to give some examples, I would know examples. So late stage pulmonary fibrosis, where the lung tissue has been replaced by scar tissue, and that could arise due to, well, some chemotherapies end up with that. It can arise from smoking, tuberculosis. In tuberculosis, what they're looking for is part of the alveoli are actually replaced by scar tissue called granulomas, where the organism is actually being encased in calcium by your immune system. And that's why it shows up on x-rays. It's your alveoli has been kind of replaced by this fibrous scar tissue, which is calcified and often containing the organism still. If the organism is killed off, you still end up with those granulomas because they're scar tissue in your lung. Lung cancer, clearly the type 1 or type 2 cells become cancerous and the alveoli are replaced by tumor. So those would all decrease the total lung capacity, total lung capacity. In the case of obstructive diseases, and I give a few examples here, the patient is unable to ventilate very as easily because the compliance is, the ventilation is unable to get through, or in the case of emphysema, the tissue isn't quite as elastic, isn't quite as compliant. And the way this is showing up in your spirometry isn't by changing the total lung capacity. That often stays pretty much the same. The main way you see it is in the speed with which someone can exhale. So just think of trying to force fluid through a narrower opening. You could use accessory muscles, which these people do, to try and force it to go out. But if you look at their forced expiratory volume, it may even be normal, but they're unable to push it out as rapidly because they can't get it, say through this narrowed opening if it's something like bronchitis. And so you look at how much air is expelled in the first second of trying to exhale. In a normal person, you can expel more than 70% of the expiratory capacity in that first second. And in someone who has obstructive diseases, they get less than 70%. So that is just a rule of thumb. It's not special. It's just a rule of thumb where they're now diagnosed as having an obstructive disease. So Kevin mimics this. If you watch the video, or when you watch the video, you'll see this by taking the tubing of the spirometer and obstructing it with, I believe, we do it with tape. I can't remember if he did it with something else that would kind of make that opening narrower. Not the whole tubing, just the access into the tubing. And, his numbers come out pretty good. He actually somewhere just under 70% normally, but, that's not because he has an obstructive disease, I'm sure. But you see a substantial drop in the FEV1 in 1 second with that disease. Okay, so what happens in these patients is often they start using accessory muscles in order to try and get the air to move, but air remains in their lungs. And as I mentioned before, early emphysema, you see this in our slide where the alveoli have not rebounded. They also tend to, in using all these accessory muscles, tend to get these barrel chests where their lungs aren't rebounding back. They're building up muscles to try and push things, and their morphology kind of changes as they try and use these extra muscles and get their lungs to rebound back. And they end up with this kind of barrel chest appearance. So that means that you'll often see an increase in the residual volume. Now, you can't really measure residual volume. Remember, that's the immovable air, but it does tend to increase in these patients. Okay, so this graph I pulled out of a paper, and it's just showing you, don't worry about exact numbers here, but here's inspiratory capacity, the expiratory reserve volume, and the residual volume of a normal young person. And that makes their total lung capacity, right? As you get older, just like in your blood vessels, your skin, elasticity decreases. So you don't see a big difference, maybe a slight difference in the total lung capacity, but see what happens is that they're unable to expire as efficiently. So you can't empty the lungs as efficiently. So residual volume goes up and the expiratory reserve volume goes down. So that's normal with aging because of those elastic fibers becoming less elastic in the lung tissue itself, even without any disease state. So here's somebody with early emphysema. So emphysema, as I mentioned, sort of bridges. Early on, it acts in some ways more like a obstructive disease, and you see residual volume going up, and total volume of the lung also going up. So they're showing this as largely a obstructive disease because compared to the normal, and I can't measure it, but ERV looks quite similar, inspiratory capacity looks quite similar, but the residual volume has increased substantially. Now, this is not plotting FEV1, right? That's not plotted here. So it's only plotting a total volume, not how much of the volume it can expel in 1 second. So once it gets severe, you can see quite a huge residual volume, lots of old air left behind, and this person is probably needing to supplement their breathing with pure oxygen because there's so much old air left behind. Even if they can breathe in a normal tidal volume, it may not make a very good gradient to get oxygen into their blood. And then they did one example of a late pulmonary fibrosis where you can see in this patient the residual volume is similar. Their lung capacity is, or their dead air in it is not changed that much, but their total lung capacity has changed. So they're mostly, that's through all three of them have really, all three of them, the inspiratory capacity and the ERV have diminished in this patient. So what you're going to do is you're going to be getting these figures that all are related to the lab manual figure that I referred to that you should really study. So I'm having you write down what their normal numbers are. I don't actually know what Kevin weighs, so I just made him 140 pounds, made a guess here. So fill this table out. You have a week to do this. It's due on the 29th. And he goes through this in the photographs. So he's not doing it in the video. This is in the photographs that I'll show you when we get to the study guide in a second. Now, why that is they must have changed the program. And so the handout didn't correlate very well to what they were doing. There's probably two exercises they would have had to do, one to measure these normal things, and then the other to imitate obstructive versus, an obstructive disease, which is the one he's doing with the video. So this one is more for the video. Now, because the lab manual doesn't talk about what normal numbers are for peak inspiratory flow, I don't have you learn those. I put big X's through them. But from all of this, you are going to get the FEV1, so you'll be able to see the effect of the obstruction being put in place. So since he has this data here, go ahead and fill out it. There's a table at the end of his video which shows all the data. It's nice not to skip to the end of the video because you get a sense of how he got to that data. And then you get to write down the effects, his normal, and then the effect of the obstruction. Okay, so that's what you're going to be doing. And just to orient you, let's stop sharing this. And I'm going to share oops, why didn't I get that one? Sorry. Too many screens to share here. This one. Okay. I guess because I know why I didn't. I have to close this one. It's there. It's just not. Okay. So this is in the study guide. Here is the YouTube video that does the obstructive restrictive, the last part, that last table, and shows you how Kevin measures it. Now, I included these other two because they do a much better discussion of just what are volumes and capacities, obstructive versus restrictive diseases. And these I got online. More complete understanding than anything he does in his video. So I would suggest maybe watching these two first and then going and watching Kevin do this. They don't show people doing it. And there is nothing in mastering. They show somebody sitting at a spirometer. You can look at it, but they don't show them measuring anything really. So I went online and I found these two to help review that for you. So once you watch him demonstrating the use of this equipment, here he is doing it, then here is some of the data that he obtained for that first table. Now I wanted to show this to you because this is a tidal volume, and what you're going to see, even though Kevin is probably not as big a person as the 500 ml would suggest, is when you do what he's doing, blowing into this tube, it is really, really hard to not blow into the tube. In theory, tidal volume is that unconscious breathing. But I tell you, as soon as you stick something in your mouth, and he's got his nose plugged so it can't go through his nose, you can't help but kind of blow into the thing that's in your mouth. And because of that, you're going to get very erratic sizes of a tidal volume. So you have a really big one here. This over here is liters, remember? And he's probably, somewhere around 500 mLs, plus or minus. But you'll see that it's almost always more than 500. Almost, it's a liter, So what I had you do is take this tracing. He took a picture of it, and don't worry about the M in this tracing. Just eyeball who you think are the three smallest ones, and then measure their height or estimate it using the scale here. Here's 500, right? So I know you won't be able to be real exact, but measure it 3 times, 3 of these, and average them. And in fact, I guess because I felt like it wasn't, I went ahead and did it. I measured them and I gave, oops, there's a typo in there, right? There's 2 dots here. I went ahead and measured. So go ahead and you just do the math and average it to get a tidal volume. Now you're going to need that tidal volume because everything else you're going to measure are largely capacities. So you're going to have to separate, do the subtraction to get rid of tidal volume and figure out what the others are. Oops. Okay, no. All right, so then after he did this breathing tidal volume, he did a major inhalation and exhalation. And one other thing I wanted to point out, and I forgot about this, is one of the challenges of doing it with this apparatus is there tends to be a little bit of drift, which means that see how 0, you would expect him to be breathing above 0 and then below 0, kind of like this first one. But as soon as you start breathing through it, you often get, it warms up actually is what happens. And you start to see the 0 is no longer matching the trace line. it's kind of gradually going up, and that has to do with, he explains it a bit, the warming up of the membrane that is being used to measure this. So that's one reason I did the measurement for you, because I kind of figured how to compensate for that drift. Luckily, when he goes to do his major inhalation, you can start from 0 here, and eyeball over here, and then measure what it is. And I think he does it for you actually with the machine, if I remember. Yes, here he does it for you. He's measuring from the exhalation prior to inhalation down to the deepest peak. So that's an expiratory reserve volume. That's a volume that the maximum he can exhale beyond normal tidal volume. So he did measure that for you, gave you that number. And I don't think he measured. Yeah, you have to estimate the height to get the inspiratory capacity. So to do that, you're going to measure from 0 and try and figure out where this meets here. Since it's at 0, that's the inspiratory capacity. If you fill out the inspiratory reserve volume, you got to subtract your average tidal volume. So that would be from wherever the average tidal volume to here. And then it says to estimate the functional vital capacity from the lowest point to here. You can measure that or estimate that roughly, because it's starting right at 0 here. So you're measuring from here to here and trying to project it over and get a functional vital capacity. Okay, we did that one. Once you've got those data in the table, you're going to do a little math as well. We're going to use his, I used the spirometer tracings to calculate approximate average respiratory rate as 12 breaths per minute for Kevin. And from that, you want to calculate his minute respiratory volume. So remember that is, the formula for that is his tidal volume, MRV, equals tidal volume times his respiratory rate. So you're getting milliliters per minute. Now, the lab manual states that on average, this is in that graph that you're studying, and table next to it, an average residual volume is about 1,200 mLs. Since we'll use that for Kevin, and since Kevin we're going to say is, I put 150 pounds, 140 here. Well, let's say he's 150 pounds. Then I want you to calculate what is his residual volume that's not in his dead space. This is his dead space volume. What remains? Okay. Perfect. And I believe that completes this table. So I will be turning you loose to work on this, and let me know if you have some questions measuring the data, how to go about it. And I'm going to be here, so just shout out, turn your mute off and shout out and ask for some help. If you'd like to get into breakout rooms and work together, you can let me know that too in chat, and I'll put you in a breakout room. I encourage you to try and finish this handout today, and then whatever time's left, you can go back and study models and work on slides if you're still doing the slides. The slides are due next Tuesday. So the histology drawings, which I know there's quite a pile of them, you're going to turn in by 5 o'clock on Tuesday. Did I get that right?
Thursday,
the 27th. That's right. Oh. And then on the 29th, as I put in announcements, there's quite a bit to turn in. You'll be turning in the spirometry handout at that point. So make sure You understand it, you can answer the questions. So on next Tuesday, we'll go over the spirometry handouts questions to make sure you have the answers to those. And we'll probably use part of the lab for lecture review. You're also turning in your lecture on the 29th, the day of the exam, your Thursday. You're turning in spirometry, you're turning in your lecture questions, which is set 5 through 9. And you are turning in an essay. And again, like last time, I will let you know while you're taking the Canvas test, I'll let you know which essay you are turning in. So are there any questions?
Professor?
Yes.
The slides that you were showing,
Did I not?
title, volume, I think we have, I don't know if we have a different version of the study guide.
No, I may not have remembered. I made them.
Okay, no worries.
Thank you, Sana. Sometimes it's all, yeah, he gave me the pictures and stuff on the weekend, and I know I've made them, but maybe I forgot to transfer that version over. So if they're not there, are there no pictures, photographs like that?
I think it has, it doesn't.
Okay.
It has 32 slides. And I think
Yeah, and this is 36. All right, sorry about that. I will get rid of the old one and insert the new one as soon as we get off. Thank you for letting me know, Sana. Everybody else would be really confused. Okay, any other issues before I go off and do that?
I also have another question. Maybe I missed this portion, but there's 2 handouts for this spirometry. Do we do both, or do we just do one?
There are 2 posted?
Yeah, there's the spirometry handout, and then there's Kevin's spirometry data.
Oh, yeah, let me get rid of, that's probably remnant from last semester that just got transferred over when I rolled over the class. Yeah, I tried to make the handout better match what you're doing. So I will make sure I get rid of that. Sorry, I guess I didn't clean up Canvas on the weekend when I got the data from Kevin. Okay, so I'll do that, and I'll put you guys in the breakout room who want to be in the breakout room. Let me just get in here to make sure you've got the right handout and all. Sorry, Siri, I didn't want you. Okay. Oh, a million announcements.